Now let us go with another example where we would like to calculate the expectation value of position x and the expectation value of momentum, and the wave function that we have is this. So what I have here is I have a constant, I have a wave function, which is function of x, and what am I supposed to do here is to obtain the expectation value. What I can say is most expected value for the position and the most expected value for the momentum. Now, for that, we understand that if I take the complex conjugate of this wave function as psi star, so what I'll have is a star e to the power of minus x squared by 2a. So this will become minus iota kx. So this is my complex conjugate of the wave function that's given out in this example. So what am I supposed to do is to find the expectation value. So I got to find x. So how do we define this? X is from minus infinity to infinity. We have psi star, and then we have the position operator, and then we have psi dx. So this should be the case. So for this, I should be using the value of wave function, which has the complex conjugate, and which is originally as a function like this. So I would be writing here a star e to the power of minus x squared by 2a, then minus iota ka times x. Then what I'll have is the psi, and that's e to the power of minus x squared by 2a squared plus iota kx. We close it down like this. So then dx. Now for multiplying the two things, what I'll get here, I have a. So what I'll get, a star will be outside, and inside I'll be left with, this is from minus infinity to plus infinity. This is minus infinity to plus infinity. So what am I going to get here is that it is e to the power of 2 times this. So that will be 2 and 2 is going to cancel. So I'll be getting minus x squared by a. That will be the case, and this minus iota k x will die with plus iota kx. So that term will not stay here. And what else I'll have is this position, and then dx. Now, talking about this standard integral, that this x will be this standard integral equals to 0. So what I get is that the position, the expectation value for the position for the given wave function is equal to 0, and we understand that this x will at infinity, the value of the wave function is going to be 0. Either you are on the plus side or on the minus side, and that argument can be used here. And so what we have is that the expectation value for the position comes out to be 0. So that's why this integral will yield us the 0 results. Now moving on, is we have to find the expectation value for momentum. So I have p, and for that, what should I do? I should write the integral from minus infinity to infinity. For that, I will have psi star, then I will have the operator of momentum, and then I will be using psi and dx. This should be the case, and here the expectation value of momentum will come out to be. So here I have minus infinity to infinity. So for psi star, I have a star e to the power of minus x square by 2a square. Okay, that is square here. Okay, so that is square. I have committed this mistake. I'm extremely sorry for that. And so what am I going to get out of this is then here I have minus iota k x. Okay, I'll close this. Then I have to use the momentum operator. And what's that equal to? That's equal to h cross by I dou by dou x of what? Dou by dou x of psi. So psi is here what? It is a e to the power of minus x square by 2a square plus iota kx. So I would bracket it out, and finally I have dx here. Okay, that's fine. So from here, what can we do is we have to calculate the expectation value for the momentum linked with this wave function. So outside we will have a star, and the multiplication of these two stars will give us a square. So that's fine, nothing wrong with that. And then I would like to keep things in the same order. E to the power of minus x square by 2a square minus iota kx. That's fine. Then this h cross by I would like to get it out. H cross by I is out. And the derivative of this exponential function will give me the same exponential function. That's e to the power of minus x square by 2a square plus iota kx. Okay, but I got to find the internal derivative of the exponent that we have here. So here I will have a bracket. To integrate this minus x square by 2a square will give me minus 2x by 2a square and plus. So I'm going to get two terms. Plus iota kx will give me iota k. And then I would like to have dx for this whole thing. So this p, the expectation value of the momentum, will be h cross by I times a square. Now we can see from here we will have two integrals, one in terms of this and another in terms of iota k. That will be the case. So when I multiply with this with this, I'm going to get the same thing, e to the power of minus 2x square by 2a square. 2 and 2 will cancel. So I will have x square by a square. And this minus iota kx will die when he's going to have to be multiplied with this iota kx. And so that will be the term. And then I will have this 2 and 2 will go, and what I'll be left with is x by some 2a square. That will be the case for first integral. And for the next one, what I'll have is plus. So I would like to multiply this because this is h cross by I, and I will have a square here. And what else I'll have is I will have the integral here minus infinity to infinity. That should be the case. And I will have a square. I have got it for. So what else I can have? It will have its own h cross. So that the h cross is given here. So here I'm gonna have is k, okay, e to the power of minus x square by a square dx. This should be the case. And we can immediately see that this is the same function that we have had for the when we try to measure the expectation value for the position, this 2a square can stand outside, but when I have its own dx, this integral immediately gives us 0. So what we are left with the expectation value of momentum is, so what am I going to get is the momentum is equal to a square is okay, and I have what else I have? I have here yeah. So here I have iota. I missed that iota, so this iota will come here, and the two iotas will cancel. So my answer will be independent of iota. So what am I going to get is, here I'm going to write minus infinity to infinity, and h cross I will take inside. This is h cross k. Then what we are going to have is e to the power of minus x square by a square dx. All right, and this expectation value for momentum, what we will get out of it, this is that that when you evaluate for the integral that's out here, we will simply come up with h cross k. So this the expectation value for momentum comes out to be h cross k, and which is evident that it should be valid for the wave packet, and the position, the expectation value for position for the wave function that was given in this problem comes out to be 0. And here what we have is that everything else that here comes out to be equal to 1. So that's why we have the expectation value for momentum equal to h cross k, and expectation value for position equal to 0.